Hello, everybody. I am Henry Chang Zhou from the University of Oxford. Today, I will present our work Monocular Teach and Repeat Navigation using a deep steering network with scale estimation. Monocular-based navigation benefits from low-cost, light-weight hardware, which can be mass-produced and quickly deployed. Visual Teach and Repeat is a paradigm where the robot is first driven via teleoperation and can then repeat the trajectory by applying corrections from visual or location residuals. It is widely used in navigation inspection robot and logistics robot for last-mile deliveries, especially in the unstructured environment. Slam-built metric map is not strictly necessary for robot navigation. Bio-inspired topological representations are naturally scalable for large-scale navigation problems. Our intuition is to combine scalable topological map-based localization with deep-learned local features and scale, in order to decompose the navigation task into a series of visual servoing subtasks within each topological node. This paper proposes a novel monocular teach and repeat navigation system with the capability of scale awareness, that is the absolute distance between observation and goal images. It decomposes the navigation task into a sequence of visual servoing subtasks to approach consecutive goal node images in a topological map. To be specific, a novel hybrid model, named Deep Steering Network, is proposed to infer the navigation primitives according to the learned local feature and scale for each visual servoing subtask. A novel architecture, scale transformer, is developed to estimate the absolute scale between the observation and goal image pair from a set of matched deep representations to assist repeating navigation. The proposed network is integrated into an onboard system deployed on a real robot to achieve real-time navigation in a real environment. Our main contributions are: firstly, a novel hybrid model, namely a deep steering network, is proposed to infer the navigation primitives, that is a sequence of linear and angular velocities to approach the nodes in a topological map. The robot angular velocity is inferred from matching of learned local features followed by histogram voting. The robot linear velocity is adjusted by applying scale estimation on the odometry monitor to select a correct topological node map. Secondly, a novel architecture, named Scale Transformer, is devised to learn absolute scale between the observation and goal image pair from the matched deep representations. It can extract co-contextual information from a set of individual representations using a self-attention mechanism to enhance the feature distinctiveness. Lastly, the deep steering model is integrated into a monocular teach and repeat navigation system, achieving scalable navigation using a topological map in real time. Benefiting from the learned geometric priors, our approach can effectively eliminate the offsets derived from an inaccurate initial pose. The key component inside our monocular teach and repeat navigation system is a hybrid model, namely a deep steering network. The deep steering network consists of three main components: 1. Learning local feature extraction and matching, 2. Scale transformer, and 3. Inference of navigation primitives. Given the map and camera image data pair, we firstly feed them into a superpoint network to extract the interest points and descriptors. Then a subsequent differentiable nearest neighbor matching matches the interest point pairs and calculate the corresponding match descriptor distance. These matched features representations are fed to the following two subnetworks for the scale and steering control inference. Most importantly, a novel architecture, named Scale Transformer, is proposed to learn the abyssal scale from a set of irregular matched correspondence representations. The network includes 3 transformer encoder stacks in series, 2 shared linear stacks at head and bottom with a shortcut skip connection, and a multi-layer perceptron at end. Inspired by the success of transformer and natural language processing, we treat the set of individual representations as a long sentence of feature representations. Thus, we employ a residual transformer encoder to aggregate the contextual cues for one representation from all the other representations to enhance feature distinctiveness. Using these enhanced feature representations, a multi-layer perceptron regression is used to predict the scale between the map image and camera image. The ground truth absolute scale can be obtained by the laser, LiDAR, Recon System indoors or GPS RTK outdoors. Meantime, a histogram voting layer is applied to the pixel visual offset features to infer the angular velocity in order to improve the robustness of autonomous navigation. Instead of adjusting the linear velocities using the estimated scale directly, we use the recorded action, but apply scale on the odometry monitor to select the correct map image. We employ a Toyota human support robot equipped with a Shin Pro live camera and a Hakuyo UST20LX laser scanner for data collection and system deployment. The RGB images were captured by the Shin camera, and the corresponding global poses were recorded by the laser scanner via MCL localization on the pre-built 2D grid map. We provide 3 experimental evaluations comparing with baselines from localization and navigation viewpoints respectively. For the localization performance, the proposed feature matching-based scale transformer network outperforms supervised and unsupervised deep visual odometry as well as feature matching-based point net regression according to the L2 norm distance offset between the predicted translation and the ground truth translation. During the first navigation experiment, we test the deep steering teach and repeat navigation starting at the exact same position as the start point of the teaching trajectory. We can see that the navigation trajectory of the proposed method follows the teaching trajectory very closely. Our method achieves satisfying absolute trajectory error and relative rotation error between the corresponding poses in the teach and repeat trajectories in both normal and large open space indoor environments. In order to increase the challenge of the navigation task, during the second navigation experiment, we test the repeat navigation starting at a position 0.5 meter left and 0.5 meter backward from the start point of the teaching trajectory. We can see that the trajectory of the proposed method converges faster than the NWL baseline to the TAW trajectory. The proposed method helps the repeating navigation catch up with the teaching navigation as quickly as possible by reducing the difference caused by the starting point offsets. The navigation performance of the proposed method is superior to that of the NWL baseline for both absolute trajectory error and relative rotation error. In conclusion, in this paper, we propose a novel monocular teach and repeat navigation method with scale estimation between observation and goal images in the topological map. The proposed deep steering network is a hybrid computational graph that encapsulates the robot heading estimation from matching the learned local features and precise topological positioning using the learned absolute scale. With the help of the learned geometric priors, our monocular navigation not only achieves satisfying navigation accuracy, but can also deal with course start pose initialization during autonomous navigation. Our system is fully integrated with ROS and the deep network runs at 20 to 30 Hz, which can satisfy the requirement of real robot navigation. We provide a demo of our visual teach and repeat navigation with deep steering network deployed in a large hall at the UTBM building. The green line is the teaching navigation trajectory and the red line is the repeating navigation trajectory. The different colors of lines in the image paragraph refer to the match descriptor distance. We can see the deep steering network provide very robust steering control and select the correct topological goal image. red line of repeater navigation trajectory is very close to the green line of teaching navigation trajectory. Finally, the robot arrives at the start point of the teaching trajectory with a square mark on the ground. Thanks for your attention.